Houston, come in. This is Arrow 220 VLS. We are go on video contact. Arrow 220 VLS, this is Houston. We have you on visual. You have the green light to continue. Houston, Arrow 220 VLS, we are proceeding with our video lecture on interpolation and divided difference tables. Copy that, we hear you loud and clear. Okay, so this is going to be our last video on the interpolation module, and we're going to talk about the divided difference approach, which is a method that involves building a table in order to do our polynomial interpolation. At the end of the day, you still end up producing a polynomial, so the end result is the same regardless of whether you use the Lagrange method, the Vandermonde method, or the divided difference methods. They just have different advantages in terms of implementation. So the first thing I want to do is talk about a different type of polynomial representation that we haven't seen yet. Now, in the linear case, let's say p sub 1 represents a linear polynomial. And I'm going to write it using the point slope form. So a sub naught plus x minus x naught times a sub 1, where a sub naught and a sub 1 are parameters of our linear function. X sub naught is some data point, and this is equivalent to y is equal to a plus x minus x sub 1. Y sub 1 times m, or something like that. It's point slope form, essentially. Now, from this form, we want to use known points. In this case, like I said, we have 2 points. We want to use known points x naught, x1. Actually, let me write the points pairs like this. Y naught and x1, y1 to find the coefficients a naught and a1. So y naught is equal to a sub 0 plus x sub 0. We need to just plug in x naught into here, minus x naught times a sub 1. This goes to 0. So we have that y naught is equal to a naught. Now we want to find y sub 1. Y sub 1 is equal to, or sorry, we don't want to find y sub 1. We want to find a sub 1. A naught plus x sub 1 minus x sub 0, or x naught, times a1. We already have that a naught is y naught, so we can rewrite this like this. And we can solve for a1. a1 is equal to y1 minus y naught over x1 minus x naught. This is what we call a divided difference. And we have a special way of writing it. It's written f bracket, and in this case it's going to be x0, x1. And then it equals exactly what you see here, except that instead of y, I'm just going to use f to denote f of x. Oops. Let me make sure I got this right. That is the divided difference for x naught, x1. And this is equal to this. You can swap the order, and it's still correct. Now, a naught equaled f of x naught. A sub 1 equaled the divided difference of x naught, x1. This first term can actually be thought of the divided difference of just a single term, but it's just the function evaluated at that point. When we are dealing only with linear interpolation, this is all you need to do. You need to find A1, A0, and A1. Let's extend this, however, to a quadratic interpolation problem. P sub 2 is equal to A0 plus x minus x0 times A1 plus, and now if you're not familiar with the form, this is, I guess it's like a telescoping series. I'm not sure that's the correct term, but basically every time you add a new term, that new term is a little bigger. So here we have x minus x0 times x minus x sub 1 times A2. If you were to do a cubic, you would have these three terms plus another term, which will have a longer product chain. The nice thing about this is that in order to increase the order of your polynomial, all you need to do is add a new term. You don't need to change any of the old existing terms that you've already gotten. And that's one of the powers of the divided difference table. You can grow it online. You can develop it live, so to speak. So I'm not going to go into a full derivation for the higher order divided differences and how we derive them. I'm just going to go with the formulas that are presented in the slides. However, at the end of this video, I will link to a very good a YouTube playlist that has a bunch of lectures on the derivation behind and the explanation behind divided difference. And I highly recommend you take a look through it. Also, if you look down in the description, I will post links to those to that playlist as well. It's just another YouTube playlist. But we have our definition here for the divided difference between two numbers. And I'm going to say that a higher order divided difference, which is written like this, is equal to f sub x1, x2 minus x0, f bracket x0, x1, all over x2 minus x0. So higher order divided differences are just, it's still the divided difference formula, but instead of using y value, you're using previous lower order divided difference values. And notice that the difference here is between the lowest x value and the highest x value. We can generalize this formula to say that any divided difference starting at x0 ending with x sub n is equal to the difference in the divided differences of f, x sub 1 all the way through x sub n, minus the divided difference of x0 all the way through x sub n minus 1. Notice here that the two divided differences, one goes from x1 to xn, the other one goes from x0 to xn minus 1. So they overlap by a very large amount. Basically, all the numbers from x1 through xn minus 1 are shared between those divided differences. It's just that one of them starts one step early, one of them ends one step late. And you divide this whole thing by x sub n minus x0. And that is your divided difference for the highest order term. Why do you need these? You use each of these divided differences in order to solve for the coefficients of your interpolating polynomial that you see over here. If we move to the next slide, here you will see the same polynomial written with, instead of a values, here we had a sub 0, a sub 1, a sub 2. Instead of that, it is written with, it is written with divided differences. So a sub 1, as we proved, is this first divided difference. A sub 2 is this divided difference, which is recursively built using the lower order divided differences. And as you move up the chain, you get higher and higher order divided differences, which in order to calculate, you need to calculate the lower order ones. And this is why you use a table. So the way we're going to go ahead and build our table is the first thing you have to do is list all your x values. So here we have 5 points. So this is a fourth order polynomial using 5 points that we are trying to interpolate. And the points start from x naught and go all the way through x4. The table, when you code this up in MATLAB, when you actually code up the table, the first column of your table is going to be your function evaluated at these points. So f naught all the way through f4. Then the second column of your table, or matrix, is going to be the divided differences for these. This is going to be the divided difference of these two elements. This is going to be the divided difference for these two elements. This is going to be the divided difference for these two elements, and so on and so on. So, for example, if we look at the formula, actually here it is right here, the divided difference for where did it go? Fx naught, Fx1. So that's this guy. That's going to be this minus this. So this term minus this term divided by this term minus this term. If you're going to do this guy, it's going to be f sub 2 minus f sub 1 divided by x sub 2 minus x sub 1. Pretty straightforward for this first column. Now the second column, and this is where the recursion comes into play, you need to use these values to calculate the divided difference. So now, for this first divided difference of x naught through x2, we need to get this divided difference, and from that subtract this divided difference, and divide it by the difference between the highest x value and the lowest x value, so x2 and x naught. And so as you go farther and farther down the columns, with each column that you go over, you grab, in order to calculate the new divided difference, you grab two old divided differences from the previous column, and you subtract them by a difference in x's, however that difference is growing. So in the first column, we're just dividing by x1 minus x naught. By the time you get to the last column, look at the first x value, it's x naught. The last x value is x4. So the very last column, to get that last divided difference, it's going to be this one minus this one. That's going to be the numerator. I'll go ahead and write that. So to get this last guy, this is going to be equal to f of x1 through x4, that divided difference, minus f x naught through x sub 3. That's a 3. All over the full range of x's. So x to the 4, x sub 4 minus x naught. So grabbing this last element and this first element. So, final one additional final recap. To get this, you use this and this and this difference. And these two guys you use to get that, and these two guys you use to get that, and so on. To get this guy, you use these two and these two. To get this guy, you use these two and these two values. If you calculate all the nice thing again about this method is that you can easily increase the complexity of your polynomial by just adding more terms. And you can keep all the old ones. They don't need to be reevaluated. So here's an example function where our polynomial fit, I guess, before I move to the example, how do you actually use this table to get all your desired a coefficients? Because at the end of the day, that's what we're trying to do. We're just trying to get these a coefficients. Well, follow the method shown here. Follow the form of the equation shown here. And you'll see that each of these divided differences, if you pay attention to those, if you go back to the previous slide, you'll see that each of those is in the top row of your divided difference table. So at the top of every single column is one of your coefficients of your polynomial. This is the a sub 0 coefficient. This is the a sub 1 coefficient. So this is a sub 0. This is a sub 1. This is a sub 2. This is a sub 3. This is a sub 4. And so to demonstrate what this looks like, here are some divided difference values. And you can see that the last coefficient is actually 0. So even though we have 1, 2, 3, 4, 5 points, we're not going to do fourth order interpolation. We're only going to do third order interpolation, which is apparent right here. You will have a coding problem on this on your homework, where you will be given certain sample points. From that, you're going to need to construct this table. And then using that table, you're going to need to be able to build this polynomial. So I recommend looking through these slides. You can also look in your textbook to learn more about divided differences. And again, I will post a link to additional explanations for how we derive these higher order divided differences. But even if you didn't watch those, just by remembering these formulas, you should be able to do the homework. And with that, we conclude the interpolation chapter. The next chapter is on linear least squares, a very exciting chapter. All right, thank you for watching.